In the previous video, we introduced the current phasor and derived the voltage phasor for a resistor in an AC circuit. And now we're adding to this by deriving the voltage phasor for an inductor. And as you can see in the intro animation, the voltage phasor for an inductor is pi over 2 or 90 degrees out of phase with the current phasor. And in fact, it leads the current phasor by this quarter cycle increment. So things are starting to get interesting. So let's get started by looking at a simple AC inductor circuit, and we'll see if we can derive this weird out of phase voltage across the inductor. So here's our circuit with just a simple sinusoidal power source and a single ideal inductor L. Now recall that our current is going to be sinusoidal as well, and we choose to give it a phase angle of 0. So all phases refer back to the current function. So now we're going to apply Kirchoff's voltage law, or KVL, to the circuit, and I'll do this in a clockwise loop. So we have a positive V of t minus L di dt, that's the induced voltage across the inductor, and this is all equal to 0. Now the voltage across the power source is the voltage across the inductor. So the voltage drop across the inductor is equal to L di dt. Now plugging in the current function, that's I cosine omega t, we need to take the time derivative of this thing, which gives us the sine function with a minus sign in front and a factor of omega due to the chain rule. So there we've just taken the derivative of the cosine function, giving us the negative of sine omega t, and then the chain rule produced that extra factor of omega out in front. So this leaves us with the voltage across the inductor as negative omega L I sine omega t. And written in terms of voltage amplitude, we can just call this negative big V sub L, that's the amplitude, times sine omega t. Now we want to relate this to the current function, and it's going to be easiest to compare if we rewrite this thing as a cosine. And here's where we recall that the negative of a sine function, so that's the white curve in this picture, the negative of a sine function is just a cosine function shifted to the left by pi over 2. So if we take that yellow, just standard cosine curve, shift it to the left by pi over 2, we get exactly the negative of a sine function. So to shift a cosine to the left by pi over 2, we add pi over 2 to its argument. So now we have the voltage across our inductor written as big V sub L, that's the voltage amplitude, times the cosine of omega t plus pi over 2. And just a reminder there, the big V sub L is omega L times I. Now we want to get an Ohm's law style relation out of this voltage amplitude. And we already see something that looks a lot like V equals IR. In other words, voltage is proportional to the current. But this time, instead of resistance, the constant of proportionality is omega times L. And that omega times L gets a special name. We're going to call that the inductive reactance. Symbolically, we write it as a big X subscript L. So the inductive reactance is omega times L. And you can view the inductive reactance as the effective resistance of an inductor in an AC circuit. So we can see in this voltage relationship that if the inductive reactance goes up, then the current must go down, given the same voltage across the inductor. So it's playing exactly the same role as resistance. But this time, our effective resistance or reactance is frequency dependent. So if omega is large, we get a large reactance. This makes sense because changing the direction of the current rapidly should induce larger back EMFs opposing the change in current. Similarly, a small omega means the current isn't changing very fast, so we get small induced EMFs and very little resistance to the change in current. Now finally, we'll go ahead and write our voltage function in terms of X sub L, the inductive reactance. So there it is, the voltage as a function of time across an inductor in an AC circuit. So it's I times X sub L times the cosine of omega t plus pi over 2. So note that this is out of phase with the current flowing in the circuit. It's actually leading the current function by a quarter cycle or pi over 2 radians. So next we want to take a look at the phasor representation of this voltage function for the inductor. So here's the static phasor representation of both the current function, as usual, tilted at an angle of omega t at this particular instant in time and having a phase angle of 0, and the voltage across the inductor. So that's shown in red with a magnitude of I times X sub L. Remember, that's the voltage amplitude of this thing. And this voltage phasor is advanced an additional angle of pi/2 or 90 degrees relative to the current phasor. Now I've already shown horizontal projections of these phasors in the picture, and recall that these projections are the part that has a physical interpretation as the values of the actual sinusoidal functions that we're trying to model. So we take a closer look at the horizontal projection of the current phasor, and that's I times the cosine of omega t as usual. And next we take a look at the horizontal projection of our voltage phasor for the inductor, and that's given by I times x sub L, again the voltage amplitude, times the cosine of omega t plus pi/2. So remember, these phasors are actually rotating with angular velocity omega, and then the values of the horizontal projections generate the sinusoidal functions represented by the phasors. So in the animation, we can watch those horizontal projections of our current phasor and voltage phasor for the inductor and generate points on the corresponding sinusoidal functions using the usual convention of rightward as positive and leftward as negative. Keep in mind this video is part of a short series on AC circuits for first year physics, and you can find a list of all those videos down there in the description. In the next video, we derive the voltage phasor for a capacitor in an AC circuit, and we're going to get another phase shifted function, but this time the voltage lags the current in the circuit. I'll post a link to that video at the upper left, and I'll see you there.